Alright, lots of stuff to go over today. Mostly we're going to talk about Verilog. I can talk a little bit about Lab 6. Lab 6 is graded and back to you if you turned it in by the time I graded it. If you turn it in late, I'll grade it once it's turned in. Lab 6 was a long lab, right? And it's really tricky to take it all the way to the Tinkercad circuit. It can be done. Okay, but you know, usually in the past these labs are done in groups and you're working with a physical protoboard, which in some ways is easier to work with than Tinkercad because you know, you have test equipment that's somehow easier to use than sort of the virtual multimeter and so on. But you know, some people did get this all the way to a working implementation in Tinkercad, which is cool. But if you didn't, right, if your circuit diagram is good, right, you get most of the points for the design and such. But any questions on either the lab or so far on Verilog, we're going to have to talk about these always blocks and about assignment statements inside always blocks and so on. But any questions up front? Alright, so before we get into the Engineering 250 part of this, I need to talk about something else. Okay? I want to say a few words about academic honesty. Particularly this quarter, because everything is online, we're relying heavily on the honor system. Okay? There's always an honor system in place at Clark and probably at any school, but especially this spring quarter, right, with exams being given online and so on, we're really putting students on their honor, okay, to work with integrity and to make sure that the work that they're turning in is their own. So homework and labs, those have been the main components of the course so far. We had a midterm, we'll have a final, but homework and labs, right, those should be your work that you're turning in. Okay, a circuit diagram that you draw, an equation you write, a paragraph that you type, that's got to be your work. Okay, if it's your name on the top of the page, it should be the stuff that you've come up with. Now, there's allowable exceptions. For example, you know, in the lab where we have a 5x5 circuit, there's a picture of the circuit wiring diagram in the lab report, and I've said you can copy and paste that, right? But remember I said put a note on the bottom saying, you know, this is taken from, you know, lab such and such, here's the website, here's when I got it, right? So you're not claiming it as your own. That's okay. But as far as, you know, writing up solutions, coming up with a state machine, coming up with a state diagram, a transition table, things like that, whatever you're turning in on your homework or labs, it's supposed to be your own work. Okay? And this is tricky because, you know, it's a collaborative environment and I want you to be able to work with other students. Okay? A lot of the valuable learning I got when I was an undergrad was by working with my friends. But that didn't mean that, you know, my friend did the assignment and I went over and said, hey, can I see your answer? And I copied it down and put my name on it. Okay? It meant that, you know, if I didn't understand what a JK flip-flop does versus a T flip-flop, I could ask my friend and he'd draw me a picture and say, see, when you do this, this happens. When you do that, that happens. And you know, or if I got an answer that didn't make sense, I could go to a friend and say, hey, you know, does this look like what you came up with? And they'd say no, and we'd compare answers, you know. I want you to be able to work with other people, okay? But you got to be careful because there's definitely a line. And if you cross that line, really bad things can happen, okay? So talk to other people to help understand concepts, to help clear up confusion, to better your grasp of what's being asked for in a question or some underlying concept, but then go and do your own work. Okay? And I would prefer, when you hit that point where something's not making sense, you're not sure what's being asked for, I would suggest your first call is to me, okay? Shoot me an email, come into office hours, ask during class, something. Because I will give you an answer that is in harmony with what I've been talking about in class, right? But which tries to understand where your confusion is and then help you move in a direction that results in less confusion, okay? If you talk to a friend, they may try to do the same thing, but they may have learned some totally different way to do this, and they may give you that totally different way, and now it's going to make even less sense when you go back and look at your notes. Or you may ask your friend, and they may not know how to do this, but they may think they do, and they may teach you a technique that's not correct. And so I'll get homeworks and I'll compare them to one another, and I'll see 5 or 6 students turning in the same incorrect solution to a problem, okay, or a lab, okay. The other alternative is people will go online, and as soon as you go online, you're going to find 20 or 30 different answers for how to make a state transition table, for how to implement a circuit with a JK flip-flop, right? And chances are none of those 20 or 30 answers is going to match what we've been doing in class. And you're just going to get further confused because every time that I talk about it, it's not going to agree with what you have done on your homework, right? And it's a big slippery slope. And my real concern with this is that, you're trying to learn this stuff so that you can move on. You're trying to get a C or better in this class so you can move on to Engineering 270, so you can move on to, the computer science sequence or the engineering sequence, so you can transfer to a university and get a bachelor's degree and go out and get a good job or go on for a master's degree or whatever it is that your dreams are, right? This is a piece of that. And your goal here is to, take care of this piece so that you can continue on your path, whatever that path may be. And when you're trying to do a homework problem, if you know how to do it, it's really just practice. It's getting faster at it, it's polishing your technique, and so on. If you know how to do a problem, you still need to do it to get the grade, but you're not really learning a whole lot by doing it. Okay, but if you encounter a problem that you do not know how to do, that is so valuable. That's the exact problem you want to spend all your time on. Because it's telling you there's something lacking in your understanding, there's some disconnect, there's some gap, there's something that you need to learn. Okay? That's not the time to decide to skip that problem, or to get the solution from a friend, or to send $15 to Chegg and download an answer, right? That's exactly the time to say, okay, I'm going to have to try to figure this out, and put your head down and work on it, and beat your head against it, and fail, and try again, and fail again, and keep working at it until you either get the answer or you decide to come to me for help. Right? Which doesn't have to be, 6 hours into this. You could ask me for help sooner rather than later. But you don't want to give up on those problems that you don't know how to solve. Those are the problems that are going to help you learn. Those are the only problems that are really going to teach you something. And it's unfortunately those exact problems that people too often lowball. They go off and they buy a solution, or they download something from somewhere, or they get somebody else to help them. So you're depriving yourself of the most valuable learning opportunities, right? And that's my real concern with people, looking at things and turning in things that potentially aren't their own. There's a bigger issue, which is when you are caught doing this, a number of things can happen. Okay, in some cases you may be given a chance to redo the assignment. That might happen at Clark. That will not happen at a university, right? You may get a 0 for the assignment. You may get an F for the course automatically. You may get kicked out of the department. You may get kicked out of the program. You may get kicked out of the school. Okay, depending on where you are. But particularly at the university level, there's very little tolerance for this. and it's very widespread. Okay, there are organized networks of students who have access to old copies of exams, old homeworks, and will contact you when you start at another school and say, hey, you know, for X amount of money, we'll give you access to this information. It's very easy to get to, right? And some people get away with it, but usually it's pretty clear to a teacher when something is going on. And if you get caught on the wrong side, right, it can be really bad. And if you're helping a friend, if a friend comes to you and says, you know, I'm really struggling with this, can I see your answer? Be really careful of that, right? You can talk to them. You can look at what they're struggling with and try to give them some help. But if you give somebody else a copy of your homework and they take a screenshot with it and they take that and turn it in as their work, you're just as liable as they are for cheating. In most cases, the teacher will see 2 copies of the same solution. Both people get a 0. And if there's an honor board situation, both get referred to the honor board. So you really, really got to be aware of this. You got to be really careful of it. And it's not necessarily that anyone's trying to do something wrong or trying to be dishonest, but there's a line there, and it's easy to slip on the wrong side of it. And you can avoid getting too close to that by coming to me if you're having trouble and saying, hey, you know, I don't know how to interpret this question, or I don't know what a JK flip-flop is, or I don't know what an AND gate is, right? I'm here to help you learn. I'm here to help you with this subject. Every teacher I've encountered at Clark is absolutely committed to the success of their students. And to whatever degree you're willing to put in the time and effort and energy to succeed, I will match you and I will meet you. Okay? All right. So that's all I'm going to say about that. If you have any questions about it, definitely let me know. But it's something that I'm seeing to a higher degree this quarter than in past quarters, possibly because, you know, we don't have the face-to-face element, and the course is going quicker because, you know, we're 8 weeks instead of 10. But just be careful of that, right? And don't hesitate to find me and ask questions if something's not clear. All right, so on to happier topics. Let's talk about Engineering 250. Let's talk about Verilog. So let me bring up the how-to Verilog business. Which I have to find because I always move it around. There it is. All right, so yeah, and some people have come to me online and screen shared they're using the ALDEC tool, and that's really an efficient way to find problems. If you can screen share with me and show me what you're doing, then it's relatively simpler for me to say, you know, try this, try that, and so on. Screenshots work sometimes, but for this stuff, it's easier to just hop online during office hours and screen share. So we've talked about, you know, the basic setup of Verilog, the module statement, and so on. And we started talking about this idea of event-based programming. So this always block. Okay. So the syntax for this is always at. And usually we say either positive edge or negative edge, followed by the name of some signal, which more often than not is going to be clock. Okay, so always at positive edge clock, begin. And begin, end are like curly brackets in C. We say begin, we list a bunch of stuff, we say end. The stuff in here is the body of that always block. And what we're saying is whatever this signal is, let's say we're doing positive edge, build me some hardware so that at the moment that this signal rises from 0 to 1, all of these things happen. All right, so what can we do in this always block? We cannot say assign, because assign says connect two wires together. And we can't conditionally connect two wires when things happen. But what we can do is we can do this other version of assignment, which is a less than sign followed by an equals. Okay, and I'm going to suggest that this is the only kind of assignment you do inside an always block. Okay, so, you know, A less than equals B. Think of this as copy B to A. It's a different feeling from assign A equals B, which says connect B to A. It's making a permanent connection so that whenever B changes, A will change accordingly. This is just saying copy from whatever this value is into that value. And later on, you know, B could change value to something else. A is not going to automatically change in response. This is a moment in time, copy from B to A, whereas assign A equal to B basically says take a wire from B, feed that to A. So anytime after I've said this, if B changes, A is going to change. Okay, so in these always blocks, we're going to do these assignment statements. And there's a name for this that we don't need to be too worried about. But this is called a non-blocking assignment statement. You can also do an equal sign, which is a blocking assignment statement. I'm not going to do that. I'll mention it once or twice as a counterexample to this, but get in the habit of always using non-blocking assignment statements. The book doesn't always do this. That's okay. I want to just use non-blocking assignments, so we don't have to worry too much about the difference between the two, but there is a difference, and we'll look at that in a bit. But inside an always block, if you want to assign, use this less than equal notation. It looks like an arrow. So this was our clocked comparator example that we already talked about on Tuesday, which basically said when the clock edge ticks from 0 to 1, look at A and B, and if they're equal, set X to 1, otherwise set X to 0. So the only time that X changes value is when the clock ticks, and its value is based on comparing A and B. And there's this declaration up here where we say register X. And that basically says X is able to remember a value. Usually that means it's going to be the output of a flip-flop. But in particular, it means X can somehow remember a value. And so when we make this assignment in response to the clock tick, right, what we're doing is causing the flip-flop's Q output to be equal to 1. And then, you know, we know flip-flops will remember that value until we change their Q output. So if it was a D flip-flop, right, this would set D equal to 1. If it was a JK flip-flop, it might set JK to 1, 0, for example. Okay, so it's a point event, a moment in time when the clock ticks. Alright, so this is just reminding you non-blocking assignments are what you should use. If you use plain old equal sign, it will work. Okay, it will compile, it will run, but there are subtle differences. Okay, so stick with this. And it's one less thing to worry about. Okay, so what does a counter look like? Here's all the Verilog you need for a counter. It's just one always block. So I've set up a reset input to force everything to 0, a clock as usual, and an output. My reset and my clock are inputs. My output is a 4-bit number, and I want to be able to remember what those 4 bits are. So I'm declaring it as a register, and this is like an array declaration in a programming language. This says there's 4 bits associated with this variable reg. And we usually number these starting from 0, and when we specify them in brackets, we would say, you know, bracket biggest number, colon, smallest number. So 3 to 0 is 3210, that's 4 bits. And the always block, very straightforward. If the reset is asserted, so I could say if reset equals 1, but I can just abbreviate it. If reset, then assign a 0 to the output. Otherwise, set the output equal to the current value of output plus 1. All right, so let's drive some of this. I'm getting better at not making this crash, but it still crashes sometimes. So let's make a new workspace. And I'll just call this count 23 because it sounds mysterious. Create an empty design. We'll use Verilog. I'll call it count 23. And we'll finish. I'll say file new Verilog source. That's not what I wanted to do. File new Verilog source. It's drive backwards day in the parking lot outside, by the way. So count 23, and let's make some inputs and outputs. So we want a reset input, we want a clock input, and we want an output which will be 4 bits going from 3 to 0. Alright, so there's the start of our Verilog code. So always at the positive edge of the clock begin. Oh no, I crashed it. There we go. If reset is equal to 1, then count is equal to 0. Yeah, look at my code, because I don't remember semicolons off the back of my head. Out is assigned to 0. There we go. Is this crashing for people in the class who are running Windows, or is it pretty stable for you?
It's been fine.
Okay, cool. So if you do this and you're missing that tab on the left, we just figured this out yesterday, a student and I working on it. Go to View and there's no design browser. Oh, that's awkward. There we go. Recent workspaces. Alright, so always at positive edge clock begin. Let's do a countdown counter, just to be different. Alright, so at the positive edge of the clock begin. If reset's equal to 1, set the output to 0. Otherwise, let's just count down. Out equals out minus 1. And I'm going to have to make my output a register instead of a wire. But let's go ahead and compile it and see what it tells us. Okay. So out is not a valid left-hand side of a procedural statement. Okay, so I can double click on that and it brings me right here. Out's not a valid left-hand side because it's a wire, and I'm trying to assign a permanent value to something that's just a wire, something that has no memory. So let's make that a register. I don't know if it's double clicking that's making it unhappy, but we'll get there. Alright, so let's declare that to be a register, and let's recompile. Out cannot be driven by both procedural and continuous. I guess when I set up the wizard, I forgot to tell it this was an output. Alright, so that compiles, 0 errors, 0 warnings. Let's simulate it. So file, new waveform, and then simulation, initialize simulation. We have to select the top level, so I'll expand this and I'll pick count 23. And I can drag these individually into here, or I should be able to just drag that name up there and get all of my inputs. So now we want to add some stimulators. So my reset, let's add a hotkey. So I'm just going to go here and I'm going to type the R button. So R is going to be what I use to toggle the reset between 0 and 1. So that while I'm simulating, I can click R and I can change the value of that signal. And then our clock, what should we drive that with? How about a clock? So we'll make a clock that toggles at 100 megahertz. So it's a 10 nanosecond clock. And our output is an output, so we won't drive that. So I can start my simulation, and you can see my clock is ticking, but my reset signal is showing a line at both the top and the bottom. It doesn't know what the value, well, it doesn't know what the value is. Maybe it does. Alright, so I'm going to hit an R and step my simulation. Okay, that R changed my reset to a 1. And I'm just going to click in here and type an R and run again, and my reset goes back down to a 0. And now what's happening, my counter is counting. So if I come back over here, my I think I can zoom in. Over here, my output was undefined. That's what the X says. And then after I hit the reset, it changed to a 0. And then when I released the reset back to a 0 right here, it started counting down. F, E, D, C, B, A, 9876, and so on. And if I step it for a little further, right, it continues counting down all the way to 0 and then goes back to F.
Is that hex?
That's in hex, yeah. And I can expand this and I can see the 4 bits that make up my output, and you can see this sort of usual staircase of different frequencies that we get. This is all 1s, this is 1110, 1101, and so on. Here's 70111, and so on. And within here, you can do things like, let me see if I can do this. Like if I right click on this and say properties, I can say display this in decimal. Right, and so now it's showing me now it's showing me 15, 14, 13, 12, and so on. So there's all kinds of options in here. But there's a good looking timing diagram set, right? All right, so pretty minimal amount of Verilog, right? And always blocked with 2 statements inside. And if for some reason you wanted to initialize your counter to 7 when you say reset, well, change your Verilog, go back to design, say compile, come over to your simulation window, say simulation restart, and start the simulation, hit an R to, you gotta click in here, hit an R to bring your reset high, hit another R to bring your reset low, and you can see it initialized to 7, and it's counting down from there. And if we step it a little further, right, it goes from 7, 6, 5, 4 down to 0, and then back to 15, and so on. So part of the idea of this is rapid prototyping, right? Being able to change your design by just typing a little bit of editing in your code, recompile, resimulate. All right, so yeah, question for the last 2 problems on homework 6. Let's take a look at that, and then let's go back to looking at this Verilog tutorial. So let's take a look at the homework. All right, so let's talk about the ALU first, question 8. Okay, and then we'll go to the traffic light. But let's just look at an ALU. Remember, an ALU is an arithmetic logic unit. It's a block that does various operations. And I believe there's a data sheet for one, yeah, 382. So this is an ALU that's available. It's a 20-pin chip, right? So it's a big one. Ground and power. Has a series of A and B inputs, A0 through 3, B0 through 3. It has some outputs, S0, 1, 2. There should be an S3 somewhere that I'm not seeing. And then function inputs, F0, F1, F2, F3. This is a chip that can do different things, okay, depending on, sorry, S is your select. So this can do different operations. If your 3 select lines are low, the operation is to clear, set the output to 0. If your select lines are set to 1, 0, 1, the output will be the sum of A and B. Okay, if your select is set to 0, 1, 0, the output will be A minus B. And so you can do addition, subtraction, A minus B or B minus A. You can do ANDs, ORs, XORs, and you can also force the output to all zeros or to all ones. Okay, that's a really useful chip. It's one piece of hardware that takes the place of a number of different operations, right? And so here's the truth table for it. It's a big truth table, right? 3 select inputs, a carry in input, and then some A and B inputs. So in Verilog, we could write a description of this behavior without having to go through the whole truth table. So we have 8 bits, and we want to add, subtract, and multiply. And we have A and B going in. And our output, which might be 16 bits, because multiplying two 8-bit numbers gives you 16 bits. Adding or subtracting, you end up with 9 bits at the most, but 16 bits will be sufficient. This is X. So let's say we just wanted to make something that could add or subtract, right? We could have, a single function input, and you set up the ports on your problem and so on, but the heart of your operation is one line. You could say assign x equals f equals, let's say that add is a 1 and subtract is a 0. So I could assign x equal to, and I could say if f is equal to 1, let's assign x equal to a plus b. Otherwise, let's assign x equal to a minus b. All right, so that's the shorthand way of saying if f equals 1, set x equal to a plus b. Otherwise, set x equal to a minus b. All right, suppose we want to also allow multiplication. So let's say f is going to be 2 bits, and if it's equal to a 2, we want to multiply. So I could do something like this. There's a question mark in here for the ternary operator. So if f is equal to 1, let's set x equal to a plus b. Otherwise, let's set x equal to the following. If f is equal to 0, a minus b. Otherwise, a times b. So it's a nested ternary operator, right? If f is 1, x will be equal to this. If f is not 1, x will be equal to this. Well, what is this? If f is 0, it's a minus b. Otherwise, it's a times b. So that's probably the most straightforward way to do that. So what does the colon mean by otherwise? So this statement here says if expression is true, then assign x equal to a, else assign x equal to b. Where a and b could be anything. They could be the name of a wire, or they could be, an expression like this. So it's separating the two possibilities for what this right-hand side is going to be. If f is 1, this right-hand side is a plus b. If f is not 1, this right-hand side is a minus b, and this says assign x equal to a minus b.
So earlier, didn't you say like we could do assignments conditionally?
Say again?
Earlier, didn't you say like we could do assignments conditionally?
Inside and always block. But you don't need
it.
it.
Why is it that like in an always block we can't do it, but in this case we can?
Because we're not asking for something that's going to happen at a point in time. We're describing what we want our circuit to look like, and we want to build a circuit so that x is either connected to the result of doing this, or the result of that, or the result of that. And so this will synthesize to, an adder, a subtractor, and a multiplier, both inputs A and B going to each, and then the output will go through a pair of multiplexers to choose which of these outputs gets sent to X.
Okay.
Okay, but in an always block, this would be easier, right? If we introduce a clock in an always block, we would basically say, feed one of these to, say, the D input of a flip-flop. And then when the clock ticks, that value gets loaded into the flip-flop.
Okay.
All right, other questions on this one? So the traffic light question, I still want you to think about this. Tuesday I will show you a solution to it, and I've already promised you I'm not going to pick this one as the one I grade. Hold on, follow-up question from the previous one. So in other words, the x will be equal to b as long as the expression does not equal the number, in which case x will equal a. So on here, x is equal to a as long as this expression is true, whatever that expression is. If it's f equals 1, right, then x would be equal to a if f was 1. And it's equal to b if this expression is false, so in this case, if f is different from 1. Cool. All right, traffic light. Think about the traffic light as a machine with 6 states. And think of the states in terms of which lane is green or yellow. Okay, there's always a lane that's either green, there's always a lane that's green or there's a lane that's yellow. And at any moment there should be exactly one lane that's green or one lane that's yellow. You should never have both of those things happening. And you should never have neither of those things happening. So we could think of our states as, you know, green west, yellow west, green south, yellow south, green east, yellow east. And we could think of our inputs as our car sensors from, say, west, south, east. And we don't need any outputs here. We could define an output based on the states. Right? So in this state, west green should be 1 and, you know, east and south red should be 1. In this state, west yellow should be 1 and east and south red should be 1, right? And so on, and everything else should be 0. So how do we transition from one state to another? Well, if we're in the eastern...
Professor,
yeah.
If you're writing something, we can't really see.
Thank you. All right. So 6 states, right? Green west, yellow west, and so on. And our transition arrows will be based on inputs west, south, east. These are the car sensors. Okay. So suppose there's a car sitting on the east, and the green east light is turned on, right? As long as there's a car to the east, we're going to stay here. So I'm going to shorthand this with some don't cares, right? Doesn't matter what west and south are. If there's a car on the east and the light on east is green, we're going to keep it green. Okay? But if there's no car to the east, but there's a car to the south, we're going to go to the yellow east. And if there's no car on the east, but there's a car to the west, we're going to go to yellow east. And if there's no car on the east, but there's cars on both the west and south, we're going to go to yellow east. Okay? Basically, if we're green, and then there's no car on the east, but there's a car somewhere else, our green light should turn yellow. And then from our yellow light, we're either going to go to here, or we're going to go to here. And which one are we going to go to? Well, let's suppose that that there's a car to the south. I could say I don't care if there's a car on the west, because west has lowest priority. If there's a car to the south, we're going to go to south green. And this is going to say even if a car leaves the east and then a new car appears, once this light turns yellow, I'm going to make this light green next. All right, but if there's no car to the south, then I can assume there's a car to the west. Then I'm going to go and turn the west light green, give that priority. And so you do this for all 6 states. Okay, it's a lot of writing, and turning this into a circuit takes a lot of work by hand, but in Verilog it's not too bad. So this is mainly an exercise about thinking about the traffic light problem from this point of view of state machines. Because in Lab 6 we didn't really do the classic state machine setup, right? We didn't really think about it in this terms. We used a trick where we looked at, the Lab 3 green and we put it through a delay circuit. So this is an opportunity to really think about it from the state machine point of view, the classic state machine perspective, as flowing from one state to another. And then if you want to try writing some Verilog for that, and if you want to try simulating it, it's really fun when you get it working. But the main benefit here is just sort of thinking about that problem from this perspective. So take it as far as you can, right? When you're out of time on your homework, then turn in what you have.
So there's like no state machine or like some kind of code for a delayed circuit?
So the idea is all of these state machines, there's a clock. Right? So with our counter there was a clock that was being fed from outside. Well, the machine that you designed for this is ultimately going to be, something with 3 car sensors and 9 lights coming out, and then a clock input, which is just a pulse train. So for this to make sense, we would want this clock to be, a 2-second period. And then, if we've got a green light and the car disappears and the car is sitting there on the south, after 2 seconds we'll go to this state, which means we'll see a yellow light. And after another 2 seconds we'll go here, which means this light turns red and the south turns green. And then we've got the 2 to 4 second transition that we wanted in Lab 6. Well, we get that by simply using a slow clock going into our machine where it ticks every 2 seconds. So that would typically be the 555 output. Does that make some sense? So what does a state machine look like in Verilog? Let me get through a little bit more of the Verilog tutorial, and then let's look at state machines in Verilog, because the ALDEC tool actually has the ability to let you define a state machine by drawing a circuit diagram. Okay, so let's wrap up a little bit more on this behavioral business, this event-based programming, and then let's have some fun with the ALDEC tool. So don't worry about simulation test benches and initial values. This was when I used to use a different tool for Lab 7. You can look at it, but we're not going to do this stuff in our Lab 7 or in our homework. I think this is a different document from what you have. I think this is a newer version. So let me just talk about these always blocks. So the other thing was, if you're doing this kind of setup, you've got to set up registers and so on and so forth. So, these states are represented by flip-flops, so we're going to have to declare registers to hold the state values. But I'll come back to that. Let's look at an always block. And let's just suppose registers have been set up and inputs and outputs are set up. if I do something like this, A gets assigned from B, what we're really synthesizing is a flip-flop with a positive edge triggered clock, which comes from this clock signal, and B is connected to the D input, and the Q output is connected to A. Okay, if we write this statement of Verilog, this is what's going to come out from the compiler. A flip-flop where the B input is feeding D and the Q output of the flip-flop is connected to A. And what's going to happen when the clock ticks, whatever value B has will get loaded into here, and A, which is connected to the Q output, will take on that value of B. And it happens at the moment that the clock ticks. And after that, if B changes, it doesn't affect A because A's value is stored inside this flip-flop. Okay, what if I also add this statement, which says that at the positive edge of the clock, A should get copied to D. So this is where it's important to remember that we're not writing code, we're designing a circuit. Because in C, if I said something like this, A equals B, D equals A, what's going to happen? Suppose B is equal to 5. This is going to set A equal to 5. And then this is going to set D equal to 5. Right? That's how code works. But this is not code. Okay, this is saying when the clock ticks, take the current value of B, copy that into A. When the clock ticks, also take the current value of A and copy it into D. So B gets copied into A, but that value of B does not also get copied into D. The current value of A gets copied into D. So this circuit would synthesize as follows. Let's bring this up here for A. And let's bring this up here for D. Right, this is the circuit that this describes. It says when the clock ticks, take the current value of B and copy that to A. Take the current value of A and copy that into D. This is a shift register. Okay, this will help you on your lab. And if I wrote Verilog code like this, right, if I write these 4 assignment statements in my always block, what this is doing is saying let's take in, feed that to the D input of a flip-flop, call the output A0, take A0, feed that to the D input of a flip-flop, call the output A1, and so on. Alright, it's a big long shift register. All the clocks get tied together as usual. We usually don't even show the clocks. And again, if this was C, right, in would copy to A0 and it would then get copied to A1 and A2 and A3. All of these would be equal to in after executing those 4 statements in C. Does not happen in Verilog, because it's not procedural. But this is a case where if you accidentally do A equals instead of A less than equals, this circuit will act totally differently. Because when you do a plain old equals sign, it does not execute these statements in parallel. It executes them sequentially. So if you just said equal, then n would get copied to A0, and then that value, which was in, would get copied to A1, and that value, which is also in, would get copied to A2, and all of these would end up being the same. And so if you wrote this always block with equal signs instead of less than equals, you get a very different circuit. You get this. Okay, don't worry too much about that. Just stick with these and remember that all of this stuff happens in parallel. Okay, and then you don't have to worry about this non-blocking versus blocking business. Okay, but this will give you a nice shift register which you can use in your lab. So that'll be helpful. All right, let's take a few minutes break. Let's come back just a little bit after 1, and we'll look at building state machines in Verilog. I'll show you how to use the tool to do that, and then we'll go on from there. All right, so meet me back here in a couple of minutes. All right, we're back. Let's play with this tool a little bit. So let me close the workspace. Let me start a new project. So we'll do a new workspace. We'll just call this state 1. This is going to be a state machine. I'm going to create an empty design. Start a Verilog module, call it state 1. Alright, so let's make a state machine, and we'll let the software do this for us, and then we'll look at the code that gets created. So I'm going to say File, New, and I'm going to say State Diagram. And I'll get my wizard as usual. So let's just make a, I don't know. Let's see if we can do a homework problem. So let's take a look at question 5. So it's a system with 4 states. Okay, 1 input variable, 1 output variable. So our input is X, our output is Z. We're going to do this in Verilog. And I'll call this state 1. So we have an input X, we have an output Z, and we're going to have an input called clock, which isn't shown on the state diagram, but we always understand that there is a clock involved. Alright, so we'll work on this picture. And I'm realizing that my resolution is really low. Okay, so that should be better. Alright, so I'm going to say next, and it's going to tell me you have not entered any clock port. Do you want clock to be a clock? And so I'm just going to say yes. So there's my block diagram, input X, output Z, single input, which is a clock. I'm going to leave everything else as is. And I'm just going to say finish. Now I'm going to come up here. Okay, there we go. Alright, so it's created a little bit of a template for me. It's got an input X, an input clock, and output Z. It's naming my module for me. It threw a little copyright down here. It's copyrighted by LDEC. That doesn't seem right because we're writing this, not LDEC. So I can go to page setup, and under table, right, I can take that off. Or I could specify something different in there. Or I could leave it, let LDEC take the credit. That's fine. So let's make some state stuff. So let's go to FSM, that's finite state machine, and I'm going to go to states, and I'm going to click on state. I'm going to drop a state down here, and one there, and one here, and one down here. And I'm going to hit escape. And I'm going to double click on this circle and bring up state properties. So my name for this is going to be reset. And my name for this state, which I'll put over here, is going to be happy. And my name here is sad. And my fourth state down here, this will be so-so. All right, so I'm mimicking this state transition table, and it's showing me in here. You know, I'm going to have two flip-flops. The value of this the flip-flops here are going to be 0, 0. This will be 0, 1, 1, 0, 1, 1. This is the state assignment table that you make in the beginning of a state synthesis problem. It doesn't have to be these state assignments. I could call happy 1, 1. I could call so-so 0, 1. Okay, but these are the default states it came up with because that was the order in which I created these dots. Okay, let's make some transitions. So I'm going to go to finite state machine, and I'm going to go to transitions, and I'm going to say transition. And let's put an arrow from here back to itself. And then I'm going to have an arrow that goes from reset to happy. So I'm just using my mouse, right? So I'm left clicking here to start drawing, and I want to come back to myself. So I'm just coming up here to put a little bit of space, and then when I left click back in a state circle, it draws an arrow. And then happy can also go to sad, and sad can stay in the sad state, but sad can also go to so-so. And then so-so can go back to sad, or so-so can go to reset. All right, so that's our diagram. Okay, well, I can click on these arrows, and this transition property, right, this is the arrow going from the reset state to the reset state. I can write some HDL, and I can say, what condition should I take? What condition should I apply here? Well, the condition is x equals 1. And the action here should be z is assigned the value 0. Okay, so that's the transition when z is when x is equal to 1, and the action is assign a 0 to z. And this arrow down here from reset to happy, right, that's going to happen if x equals 0, and the action to take is z is assigned to 1, and so on. So we can set up all of these transitions. So this arrow up here was x equals 1, and the action is z is a 0. This arrow is x equals 0, and the action is z is 1. And you know, you can put comments in here and change the line colors and do all kinds of things. Okay, and most tools that let you do things like Verilog have a whole bunch of tools built in that let you do things like, you know, describe a state machine, and so on and so forth. And it varies from one tool to another. Alright, so sad to so, this happens when x equals 1, and the action is z gets assigned a 1. And from so, if x is equal to 1, we'll assign z a 0 and go back to sad. And from so, if x is equal to 0, we'll assign z a 1. Alright, and I'm just Control-S-ing to save, because I want to save my work, especially since I know that my implementation of this tool tends to crash. Save your work often. Okay, and you know, I can take these things and I can move them around if I want, and you know, if I didn't know where these were going to be ahead of time and I put them in a spot where there are lots of things crossing, I can make adjustments like this and so on. So it's a pretty versatile tool. So this should look like yeah, that's really fun to do. Alright, so this should look like the diagram we started with. Alright, let's compile this. I'm going to go to design and I'm going to say compile. Amazingly, it worked with 0 errors, 0 warnings. That's surprising to me. So let's come in here and let's expand this over in the design browser, and there's a file called state1.v. So Verilog files usually have an extension of .v, and this file was not written by us. This was written by the tool that lets us do this layout. So let's look at the Verilog corresponding to this state diagram. So there's the module declaration, inputs of x and clock, output of z. X and clock are wires, z is a register. Right? Why is it a register? Because we're going to assign it a value as the clock ticks and we move from one state to another. Alright, so there's some defined statements. We've set up logical names for bit combinations. The word reset means the 2 bits 0, 0. The word happy means the 2 bits 0, 1. So this 2 quote B means 2 bits, and the bit pattern is 0, 1. The word sad means 1, 0, and the word so means 1, 1. So we don't have to remember, you know, that happy is 0, 1. We can actually use single quote happy, and that'll get replaced by a 0, 1. So if you've done CSE 121, this is like a number sign define. Okay, it's basically a macro kind of substitution. And we have a pair of 2-bit registers. We have a register called current state and a register called next state. Sound familiar? Right? This is part of your state transition table. Can we write all of our Verilog with state machines? No, so I don't want you to use this tool when you're writing the answers to state machine questions. I want you to do it kind of barehanded. But I want you to know this is here. So when you do the state diagram first, the Verilog code will automatically define what the circuit is supposed to do. Yeah, if you start off by making this diagram, right, the tool itself, the software tool, writes this Verilog for you. And this Verilog will achieve this kind of behavior. Alright, so let's see how that works. Always at this is whenever x changes, or current state. I don't know what that means. I guess I didn't set up the clock. So this should be always at the positive edge of the clock. Begin. Alright, so what does it do? Basically it's a case statement. It's a bunch of if statements which says if the current state is reset, and if x is equal to 1, set the next state to reset and set the output to 0. So if the current state is reset and x equals 1, current state is reset, x equals 1, set the next state to reset, set z equal to 0. Okay, that's exactly what this does. Next state is reset, z is equal to 0. If the current state is reset, and x is equal to 0, set the next state to happy and set z equal to 1. Well, that's this right here. Current state is reset, x is 0, set next state to happy, and z equal to 1. So, yeah, I know you had problems. We'll come back. Oh, it's going to make me close it. Okay, I'm fine with that. We'll get back there quickly. Alright, so this is describing your state transitions, right? If your current state is happy and x is 1, your next state is happy and z is 0. If your current state is sad and x is 1, then your next state's going to be so-so, and z will be a 1. So this is just a shorthand way of writing a bunch of if statements, okay? It's a case statement. Again, if you've done 121, this is like a switch statement in C. But you can expand it to a bunch of if-thens. So when the clock ticks, the current state and the input are used to determine the next state and the output. And then, okay, I see what it's doing. So this happens anytime that x changes. So when the clock ticks, the current state is set equal to whatever the next state is. Right? So this logic up here is basically saying, you know, when x changes or the current state changes, let's figure out what the next state is and what the z output is. And then when the clock ticks, whatever the next state is supposed to be, that gets loaded into the current state. Okay, that's the flip-flop action. And that's all there is to making a state machine in Verilog. So this is the combinational logic that goes into, you know, describing the next state in terms of the current state. And this is the action that happens when the clock ticks. And this goes all the way back to our first diagram of a state machine, where we had a memory. We had this random combinational logic with some set of outputs going back into the inputs of the flip-flop. We had some sort of outputs coming from the combinational logic and some set of inputs coming in. And when you design a state machine, as you've done in your homework assignment, right, you were making that big transition table. Ultimately, you came up with equations for, say, J1, J2, K1, K2, right? Those are the equations for what you're going to feed into those flip-flop inputs. Here's the Q1, Q2 coming out of the flip-flops, feeding that combinational logic. This is your Z equals, and X is one of the inputs that you might use to come up with those equations. And this corresponds strictly to this, right? All of this stuff up here, that's that combinational logic. That's figuring out what the next state should be. And then, you know, the flip-flop memory, that's where the clock goes in. Well, that's the part that activates when the clock ticks and everything gets loaded in and you're in the new state of the machine. So this is kind of cool, right? And under properties, I can change my encoding. If I want to use one hot encoding, I can apply that. And now you can see that each of these states corresponds to a particular pattern of 4 flip-flops, where exactly one flip-flop is 1 and all the others are 0. And if I compile that, and I look at my source code, you can see my states are 4-bit values, but most of this logic is exactly the same. If I'm in the reset state and x is 1, set the next state to reset. Otherwise, set the next state to happy, and so on. The only thing that's changed is, what does it mean when I say set the next state to reset? It means set the next state to 0, 0, 0, 1. So we can define what kind of encoding we want. Traditional binary, we can use gray encoding where it tries to move in gray code, and so on and so forth. I think user defined might let us specify our own state assignments, but I've never tried it. And the clock name, and we can define a reset condition, so we can have a reset line that forces the system into a particular initial state, and we could specify that in here, and so on and so forth. All right, so that's a nice feature of the LDEC tools. And if you want to play with this, you can play with this to work on your traffic light signal. That would be a reasonable use of it. Because, you know, the main thing I want you to think about for the traffic light question, I think that was question 7, is the state transitions, right? But then if you want to play with converting that into Verilog, I'm okay if you want to try doing that using the state machine synthesizer. So that could be fun. All right, so questions about this? Let's see, should we still turn in what we got from LDEC if it doesn't turn out the way we wanted to? Are you asking about homework or lab? And the answer is yes for both. But, you know, feel free to put in there what you were expecting it to do and what it did instead and what you think might have gone wrong, and you know, talk to me about it. Because homework's not just right or wrong, okay? But then definitely in the lab, right, definitely there's you know, experiment and observation. And your experiment might be set up wrong, but your observation is whatever you observed, right? So in the lab, you definitely want to always talk about what you actually saw, and then discuss, you know, if that was different from what you expected, why do you think that is, what did you try, and so on and so forth. So Verilog is, you know, in many ways it's sheltering us from this kind of thing, right? This might be what's being built when we, you know, actually synthesize a piece of hardware using Verilog, but we don't think of it like that. We're not thinking of individual gates and flip-flops and stuff, right? We're thinking of it perhaps as, you know, if our state is happy and x is 0, set the next state to happy. Or, you know, perhaps we're actually thinking of it like this. And Verilog is this glue that lets us, you know, sort of go from this is what we want to how do we actually make this happen. We do this in programming all the time. Okay, so Engineering 270, you're going to learn assembly language and machine language programming. Those are the lowest level instructions that the hardware actually understands. It's the ones and zeros. Okay, if you've ever tried to look at the contents of an executable file, you see a whole bunch of gibberish because it's binary code. Well, in 270 we learn how to write that binary code. Okay, how to write the actual ones and zeros that the system understands. And what we've done most of this course is basically at the same level as the ones and zeros in programming. It's the low level stuff, it's the actual hardware. This is more of a higher level version, right? Because we don't want to write binary code all our lives. We don't want to try to make a video game by writing ones and zeros in binary or even assembly language. So we use C or C++ or Java or something else, right? And so this is a higher level way to get to those low level circuits, and this is an even higher level way to get to this, which takes us into the low level hardware. So let's see a comment for me. It's harder to go from a transition to paper and Tinkercad to Verilog, but it's a learning process. Yeah, definitely. And it takes practice, and I told you in the beginning that it probably took me a few years before I actually felt like I knew what the heck I was doing with Verilog. And I'm not talking about, you know, being proficient and remembering the syntax and where the semicolons go and so on. I'm talking about a basic understanding of like what is Verilog. Really took me a few years to get, and I came back to it time and again, you know, every now and then before it started to settle in. It's just a very different way of thinking about things. So it is a learning process, and you may not encounter it again. Okay, if you're a computer science track, you may never do Verilog again. On the other hand, I was out on a run a number of years ago. I was running by Lacamas Lake, and coming down the trail from the other way, this guy stops me and he's like, "Hey, Dr. Macias," and it was a former student, and he had just started a new job, and his first day he was in a conference room with a bunch of people, and they were all talking about Verilog and writing it on the board. And he said he actually knew what they were talking about, and that was really cool. So you never know when this stuff will pop up. All right, so question here: what's the advantage of learning assembly code? Isn't it different for every processor? Yes. So each process. So assembly code is the low-level stuff that looks like gibberish, but you can learn to read it. Okay, it's one level above machine code, which is really just ones and zeros. And assembly code is different from one machine to another, but the kinds of things you do in one assembly language are very similar to what you do in another assembly language. And so learning to think at that level will help you, you know, if you try to learn how to work on a different processor, it's a familiar experience. But more importantly than that, knowing what's going on at the hardware level helps you work at the higher level. Okay, the reason we make you go through truth tables and K-maps and all of that before getting you to Verilog is not just to be mean. Okay, the reason we're doing that is because you have to understand truth tables and K-maps and assignments and all that kind of stuff in order to be good at using Verilog. Okay, to be really good at programming in C, you have to understand assembly language, because C is just a more human readable version of assembly language. And if you know how to work in C, then you can work in, you know, Java, Python, whatever your favorite more modern language is. So it's learning the fundamentals, right? And those cut across the particular different languages for different processors. It's looking at how memory is organized, what the CPU does when it tries to execute an instruction, how things get pipelined, all this sort of stuff. It's really fun stuff. If you like playing chess, you'll love assembly language, but it's good for a number of reasons. So Verilog is a pretty popular language. We used to teach VHDL, and when I started teaching this course, I talked to my advisor from grad school, who's an electrical engineer, and we talked about hardware definition languages. I asked him which one he thought was more popular. He said he's seeing a real shift towards Verilog. This was a number of years ago, but it seems to have continued. But you know, if you know Verilog, you can learn VHDL and vice versa. So there's a project called Open Cores. Okay, you can go to opencores.org, and you can sign up for an account. It's free. They don't spam you and so on and so forth. But people basically share Verilog designs on this website. And so, for example, if I'm looking for an arithmetic core, I can come in here, and you can see the licensing agreements for these. Most of these are some version of GPL that's basically an open source license. And let's say we want, I don't know, a floating point accelerator. So something that does, you know, addition and subtraction stuff of real numbers. So I can come in here. It's written in Verilog. I can say download. I think I have to get an account to download. Yeah, I don't have my account. But we can pull down the source code in Verilog for all these different projects. Right? So if you're building something, like say you want to make a Super Mario simulator, and you need to do some floating point operations, you don't have to design the floating point stuff yourself. You can pull it down from Open Cores. Or if you need a CPU, right? Something that will let you load code into it. Here's a 16-bit microcontroller. Here's a 32-bit processor, right? And these things are open. You get the source code, you can use them under very generous license terms, right? You don't have to pay for them and so on and so forth. 8080, right? So that was the first real sort of popular 8-bit microprocessor. Z80 was the one that was used in TRS-80s and was used in a lot of cash registers, and you can still find Z80s available online. You can download Verilog for that. And what do you do with this Verilog code? Well, we know we can simulate it, right? But you can actually build a piece of hardware out of this Verilog. So hold on one second. Let me grab something to show you. It's remarkable this didn't take like 30 minutes to find. So here's a circuit board. And I bought this a number of years ago from Amazon. I think it was like $30 or $35. Relatively inexpensive. And it's got, you know, some push buttons. It's got some of these 7-segment displays. It's got these tiny little slide switches on the side. It's got a VGA port, an audio port, a micro SD slot. Power goes in on the side over here. And in the middle of all this chip right here, this is what's called an FPGA. It's a field programmable gate array. And I don't know if I can get a good focus on it. That's pretty good. Okay, all these little things on the side, those are pins. So the chips we're using in Tinkercad, or that you might have used in 120, usually 14 pins, sometimes 16 pins. This thing has got, you know, a few hundred pins on it. And each of those little lines is a separate input or output or control pin to this chip. And you can see it's labeled. There's a little tiny U1 right there on the board. That's the component ID. Right? So there's a schematic you can download for this, and it'll list U1 is this chip. And this is made by a company called Xilinx, and it's a chip called a Spartan. And it's Spartan because it's an affordable version of this chip, which is a field programmable gate array. Well, here's what you can do with FPGAs. You can design your circuit using, you know, something like your LDEC tool, or you can download a design and load that into the LDEC tool and compile it. And you can simulate it, but you can also say, hey, I want to take this design and I want to load it into this physical piece of hardware. And with this board, what you basically do is you plug a USB cable in right here, and you run the right kind of software, and the LDEC tool that we have doesn't do this, but there is software that'll do this, and it compiles your design, and then it figures out how to configure this device. And what is this device? Well, it's kind of like programmable logic arrays that we've worked with a few weeks ago, where you have, you know, an AND plane, and you have an OR plane, and so on. But it's also got a bunch of flip-flops inside, and it's got some fancy hardware like some multipliers and things like that, and it has a whole bunch of multiplexers and demultiplexers. And what you can do is you can say, hey, you know, take this flip-flops input and connect it to this little piece of programmable logic which acts like an AND gate, where the two inputs come from here and here, and connect this to the output of this flip-flop, and connect this to a pin on the side of the chip, right? And you can build a piece of hardware. So it's kind of like an Arduino, but it's different in the sense that, you know, Arduino is programmed in C, FPGAs are programmed in Verilog. So the Verilog code that I write would describe a circuit, and then I can run software that will configure all of this hardware inside here to basically implement that circuit in hardware. And when you're done, you have an actual physical implementation of, you know, a silicon design that you've put together with Verilog. And it doesn't simulate it by going through step by step the way that the simulator does here when I make a simulation waveform. It actually it configures physical hardware. Right? It actually wires up these physical devices inside here to implement the circuit that you've described. And FPGAs are wonderful devices. They've been around for a long time. They picked up a lot of popularity throughout the 80s when a little company named Cisco started using them to build what they called a router, and you know, that caught on, and that really fueled the FPGA market, brought them to where they were commercially viable for a lot of people. This is custom hardware. Okay, if you have a design and you want to build an actual chip to implement it, it costs typically, you know, I don't know, a few $1 million to make one of these chips. It's a very expensive process. An FPGA you buy for a few bucks, you load your configuration into it, and it does the same thing. It's fast, it's compact, doesn't have wires sticking out of the top that can get pulled out, right? But it lets you design custom circuitry. And on this board, you know, the push buttons and the switches and the LEDs and so on are connected to some of these pins, which I can get to from my design. And I can build a circuit which says, you know, take these two switches and those two switches and add them together, and take the result and display it on this 7-segment display. And it's very few lines of code. And there's all kinds of boards like this you can get. They come in all kinds of different sizes and shapes and flavors, and they have different kinds of these programmable chips. This one is super affordable. Like I say, it was $30-some from Amazon. Whereas when I was first playing around with these things, a board like this would have cost, you know, $5,000. And they can be fragile. You can program in a way that you can program them in a way that will physically damage the FPGA. Because if you load in, you know, the right or the wrong configuration, you can do things like take outputs and connect them to each other. And if this is outputting a logic 1 and this is outputting a logic 0, you're basically creating a short from power to ground. And if you do that too many places in here, it's not unheard of for flames to come out of these chips for a little while, and then they're done. Because it's actually hardware that you're like tailoring through software configuration. So FPGAs are cool. We don't go into FPGAs here. In the past, we have done some of this in Engineering 250 with an 8-week term. That was too short to get into it here. But, you know, if you go the electrical engineering route, you'll almost definitely get into some FPGA work. If you go the computer science work, you may not get into it in your coursework, but you can still do it on your own, right? Last year at Clark, usually people work on their service learning project. It's a year-long project. I've had students who build their project around the idea of using an FPGA just because, you know, it seemed cool to them. They wanted to go further into it. So, so that's something to know about. And I have some software. I don't have it ready to go today, but I'll try to fire it up for Tuesday. That lets us take Verilog and compile it. Instead of on this ALDEC tool for a simulator, lets us compile it to download into this board. And that software is nice because you can actually go in and look at the actual picture of gates, the wiring diagram for the circuit that's being described. And that can be useful to see. All right. Questions, comments, curiosities? So keep going on the homework and the lab. Catch me in office hours if you have questions. And Tuesday we will look at a little bit more software from this. I'll talk about some of the stuff in Chapter 9. I want to talk a little bit about things like making a subtraction circuit, looking at doing higher speed arithmetic, things like that. So we'll just kind of wrap up some of these extra topics that we may not have gotten to. And then Thursday we can spend just kind of reviewing the whole course. We can talk about logistics for the final, and any lingering questions can come up during any of that. Basically got 2 classes left, so we're almost at the end of this. All right, I'll call it good there. So have a good rest of the day, have a good rest of the week, and I will see you next time.
Have a good day.
Thank you, you too.